welcome you to the UNU-INWEH public event, the Science Talk. For those joining us for the first time, you're welcome. We're glad that you can join us today. Thank you. I am your host, Professor Grace Oluwasoya. Before presenting our distinguished speaker for this morning, please note that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions. Please use the Q&A chat box, type your questions or comments in. We will pick them from there at the end of the presentation. Thank you. The topic of today's talk is Mountains as Groundwater Soil, a Canadian Rocky Mountain example. So let's talk. Our presenter for today is none other than the distinguished Professor Kathy Ryan. She is a professor at the Department of Health, Energy and Environment, University of Calgary. In fact, University of Calgary is the first United Nations University hub, and we're proud to have her here with us. She has had the privilege of supervising more than 100 students and postdocs in primarily field-based research projects. She has conducted research in groundwater, surface water, and water quality on both sides of the continent divide, in Canada and internationally, for more than 30 years. She is a member of the International Association of Hydrogeologists, Canadian National Congress, and Pub Committee, working to have groundwater meaningfully incorporated in Canada's national freshwater agenda, demonstrating clearly that she identifies as a groundwater advocate in the water cycle world. So we have Professor Kathy Ryan. You have the floor now. You're welcome.
You are muted.
Okay, I'm now unmuted.
Fantastic.
Just let me reshare my presentation here.
Please reshare your presentation.
I'm sorry about that. Thank you very much, Grace, for that wonderful talk. And I had everything ready to go except for the mute.
It's okay.
This should be.
Yeah.
And I'll put it in presenter mode.
And you're good to go. Fantastic.
Do I need to swap displays? I think I do, don't I? Better?
Yeah, you're good actually.
Okay, let's start from the beginning. Thank you very much, Grace, for that wonderful introduction. I'm really pleased to be here to talk about my favorite scientific field, which is groundwater, which, as we were discussing before we started, tends to fly under the radar and is underappreciated in its importance, not just in supplying the world, but also in supply the world. Half of the world drinks groundwater as a household water supply, but also in supplying much of the surface water in lakes and rivers that the other half of the world depends on. So before I start, I want to pay homage to our Indigenous communities here in Canada. We are in a process of reconciliation, which will be a long and difficult process. And so I acknowledge that I'm joining you today from the land of a number of nations. And this is a map that shows historically what the First Nation territories were. And I bring this map up here in the context of their water supply. So historically, nations would travel around different places, and much of that travel was for food, and much of it was also to be able to find water in the different seasons of Canada, which includes a lot of frozen months. So in this part of the world, the average daily temperature is below zero for about 5 or 6 months a year. And these First Nation communities have significant water issues. And much of that has to do with our colonial history. So this is now where there are First Nation communities, and these First Nation communities are largely on reservations, and the reservations were not designed in the context of water supplies like their traditional territories. Okay, so just before I start talking about groundwater, I also want to give a shout out to a wonderful team that I have been working with for much of this work, which is funded by Alberta Innovates, a provincial organization called Integrated Eastern Slopes of the Rockies, and you'll see why we're the Eastern Slopes of the Rockies in a moment. Climate, groundwater, surface water assessment. And remarkably, this team is led by 5 PhD female scientists, which is the first time in my career that I have worked with a significantly female team. Oh, groundwater now. So groundwater not only supplies 50% of the world's population, it also is a very significant fraction of the world's water. So you'll see here that 95% of the water supply is in the oceans. It's salty, too salty to drink. Of the 2.5% that is fresh water, then 2/3 of it, more than 2/3 of it is frozen. Most of that frozen water is in the polar ice caps, not in the continental glaciers that I'll be talking about in a moment. And a very small fraction, 0.4%, is in lakes and rivers, and most of the usable unfrozen groundwater, fresh water, is groundwater. So we don't see it the way that we see lakes, rivers, and ice, but it's a very significant and therefore important part of the freshwater budget in the world. So speaking for Canada, groundwater in Canada, lots of people know Canada as a country with water in abundance. And because there's so much surface water relative to many nations in the world, about 1/3 of us, or 30%, rely on groundwater for household water supply. And this is a map that's been around for decades. It was first made in 1996. And honestly, I don't think that Canadians really know what these numbers are anymore and how accurate the 30% is. But it is regionally variable. So our smallest province, PEI, is 100% groundwater reliant. Everybody who lives there only drinks groundwater supply. And this Yukon territory up in the northwest here, although this map says it's 48% groundwater dependent, in fact, the senior hydrogeologist that works there tells me that it's 97% groundwater dependent. And as I mentioned earlier, it's not just the people who rely on groundwater for a water supply. It also is true that groundwater supplies also a poorly constrained but significant fraction of surface water. So 20 to 80% of rivers and lakes are supplied by groundwater. And in the wintertime, when we take, in Calgary and in most Canadian cities, when we take water from our river, almost all of that river is being supplied in the winter by groundwater. If we didn't have groundwater, we wouldn't have river water supply in the river. And it's also critical to fish habitat. So it's fish biologists will tell you that fish like to lay their eggs in parts of the riverbed that groundwater is flowing into, because that has a consistent temperature. And also the cooler groundwater in the summer and the warmer groundwater in the winter are critical to modulating the temperature. And Grace mentioned that I'm part of a committee that is lobbying the federal government in Canada to show more leadership in groundwater. So we have a new Canada Water Agency, which is working towards integrating the multidisciplinary, multi-ministerial, multi-department entity, which is water. And so we have had some success this year insofar as there's now a little chapter in the annual report to our federal government that talks about groundwater for the first time in 2024. And personally, I would like to see more than 0.3% of all of our National Hydrological Services monitoring points on groundwater, given that it supplies 30% of our population and also quite a lot of our surface water. And it's really a little bit complicated. This is another talk by another expert here, but it's really complicated in Canada because water allocation and management is not national, it's sub-jurisdictional. So it's up to our 13 provinces and territories to manage and allocate the water supplies, both surface water and groundwater. So that makes the federal sub-jurisdictional relationship complex. But I will say that anybody who relies on a water well for their water supply knows the true value of water. Okay, and then going back to, I think, grade 7 in my education, and who knows what grade for everybody else's, but we often forget, those of us who work in water often forget that we are part of a water cycle, and we should be working particularly hard to talk to folks that are working in the adjacent parcels of the water cycle. So of that water that exists in the earth, 97% of it is in the ocean. The sun evaporates it, brings it down. You'll see here that in the mountains, they have water storage in ice and snow. And I beg to say that there's a lot more water storage at any given time with longer residence times in the groundwater, which is noted down here. And some of that water goes directly into rivers. Much of it goes into the subsurface and supplies the groundwater storage, which then discharges in various flow paths, some of which are short or local flow paths, and some of which are long or regional flow paths to supply lakes and rivers. One last comment about Canadian groundwater management. So in the US, which is to the south of us, which is more groundwater dependent, I think 40 or 45% groundwater dependent, there's a national monitoring network. In Canada, we don't have a significant national monitoring network, and this network has allowed the states to assess its groundwater situation from a national point of view. And it's not pretty, and insofar as the New York Times used the publicly available data from this network to have a series on groundwater to show that this is a significant concern that should be addressed. And in Canada, you'll see here, this is one of our local municipal governments, not even provincial, where they are taking groundwater monitoring on themselves because there's concern, but no national monitoring network. Okay, so this talk is about the fact that, in my view, mountain water towers are really groundwater mountain water towers. And so I found myself thinking, well, I should figure out where this term mountain water tower, which we all hear and we all relate to because mountains are such tangible things and big rivers flow out of mountains and these rivers supply much of the population in the lowland areas around mountains. I thought maybe I should try to find out where this mountain water tower term originated. And it seems that it was a resolution that was adopted by the UN General Assembly on the heels of the International Year of the Mountains, which was 2002. So the resolution was adopted in 2008, and it recognized the global importance of mountains as the source of most of the Earth's fresh water. In a time when there's a growing demand for natural resources and particularly water. So water shortages are becoming more clear and more frequent worldwide. And then they note that the retreat of mountain glaciers and changes in seasonal runoff because of climate change may impact major sources of fresh water in the world. And so what started with the UN here has now become a significant area in the natural science literature. And if you search on mountain water towers, you'll find some some of the most highly cited papers include Mountains of the World, Water Towers for Humanity, Importance and Vulnerability of the World's Water Towers. And like so much of the attention that goes into water, groundwater is pretty significantly underrepresented, given how much of the mountain water tower storage and release it contains. So here's not a very scientific, but I think a pretty telling way of showing how underrepresented groundwater is in mountain water towers. So this is simply a Google Scholar search on mountain water tower, which showed more than 500,000 results. And then Mountain Water Tower River showed 360,000, snow 174,000, glacier 40, and the lowest amount of hits for the term groundwater, which was 31,000. So about a tenth the number of papers on groundwater in mountain water towers compared to rivers in mountain water towers. And this is now slowly starting to change. So there's a few papers that have come out in the last 4 or 5 years, which are turning, I hope, turning the tide, if you will pardon the pun, which is talking about groundwater in the mountain water towers. And these tend to be in the alpine or very high mountain environments. And I'm going to move from this into the mountain block as a groundwater source shortly. So this is my colleague at the University of Calgary who has been working up in the high alpine for decades now. And the comment in the beginning of Masaki Hayashi's paper is that groundwater storage in alpine watersheds was long considered negligible, but recent field-based studies have shown that aquifers are ubiquitous. And Lauren Summers and Jeff McKenzie from McGill did a lovely review paper of groundwater in high mountain environments, where they showed that groundwater contribution to mountain stream flow, once assumed to be relatively small, is now understood to represent an important water source to streams. And in each of these papers, a critical part is the conceptual diagrams, because the truth is that there are hardly any groundwater monitoring wells in the high alpine. It's hard to get drilling rigs up there. People don't tend to live in the high alpine, and so there aren't water wells, etc. So in every one of these papers, drawing these conceptual models is really critical to increasing our understanding and insight and putting together the pieces for a puzzle that we don't have very much data for. And you'll see in this case, you know, there's short flow paths and long flow paths, and it's these moderate to long flow paths that are quite difficult to understand. And just in the last month, in time for this wonderful talk here, there's another review paper on the cryosphere. So that's up in the permafrost zone. Groundwater connectivity is a missing link in the mountain water cycle. So this paper says that mountain cryosphere and groundwater play pivotal roles in shaping the hydrological cycle, and yet their connectivity remains incompletely understood. And some more wonderful diagrams to be seen in this paper, I'm happy to say. Okay, so these three review papers have focused on the high alpine, up where there are glaciers and permafrost zones and local flow systems. And then there's another body of literature which is focusing on the mountain block, we call it. So the mountain block goes from the high alpine into the lowland areas. This is a common representation of the mountain block based on the particular geographic location in the United States, which will need to be adapted for different geologies and different subsurface hydrogeologies. But now we also talk about mountain front recharge, which is stream infiltration into the mountain zone, and mountain block recharge, which are these long subsurface paths that supply rivers and lakes downstream, and maybe both of them. So it's this subsurface pathways of how the mountain block contributes to streams and lakes, with the stream flow or the river flow getting bigger and bigger as streams flow through the mountains usually. That's the part that I think is one of the least understood areas, in part because it's so hard to get field data. And then add on to this. So if we talked about the water cycle and we talked about the fact that there's a real need to recognize, as a hydrogeologist, it's not just the subsurface that matters, it's the water coming into the subsurface, which we call groundwater recharge, or the water leaving the subsurface to supply rivers and lakes, which we could call exfiltration, that I need to talk to the different fields. Probably the largest area of water research is river flow modeling and prediction, and they have been struggling with what they call the old water paradox for a few decades now, with still work to be done, which means that the hydrogeology field needs to interface with the surface water field. And, there's a quite well-known paper by Kirchner in 2003 in which he said perhaps the kindest thing we can say about the current state of why, when it rains, the river flow goes up very quickly, but the water is not the same as the precipitation. In fact, it's some kind of groundwater coming into the stream. The mechanisms by which catchments store water for extended periods, but then release it promptly during storm events, are not well understood. And Jeff McDonnell, a Canadian hydrogeologist of great repute, said, we may be able to predict stream flow well, but for the wrong reason. So it's that understanding of the subsurface which is eluding the flow prediction models. And this is still the case today, that despite their importance, mountain hydrogeology systems are poorly understood. And in particular, understanding how geology, geomorphology, climate, groundwater flow, and related variables is barely understood. So that's the challenge that I think should be at the forefront of water resource people at present. Okay, so I want to bring you to my watershed, which is the Bow River watershed in Canada. So here's a map of Canada with the major water systems. And the boundary here between the red and the yellow is the continental divide. So everything to the east of this flows either into Hudson's Bay or into the Arctic Ocean, and everything west of it flows to the Pacific. And so the Bow River is in southern Alberta. This is the province of Alberta here, and it flows from the Rocky Mountains eastern slopes, so the western slopes flow to the Pacific, and joins with the Oldman to become the South Saskatchewan River, which joins to become the North Saskatchewan River, goes through Lake Winnipeg, and then into Hudson's Bay. And it's a 25,000 square kilometer river that goes over several hundred kilometers. So here's a blow up from the local watershed council, and you can see that in behind here there's the topography. So here's the Rocky Mountains. This is the continental divide with the headwater regions up in the divide. And I'd like to make a distinction here between the headwaters. So the headwater of Bow River is up in Banff National Park, and there's something called Bow Lake, which is widely recognized as the headwaters, even though the headwaters to Bow Lake are up in the highest elevation reaches. But the flow generation in this river continues all the way along its main stem and its tributaries pretty much until it reaches the edge of the deformed belt, or the edge of the mountains. A little bit more after the mountains, but not much. So most of this blue area here, which is the mountain reaches, is the areas in which flow increases with distance in the main stem river. And so what arrives here in Calgary, which is more than 1 million people supplied from the Bow River and its tributary, which I'm also going to talk about, which is the Elbow River. More than 95% of it was generated up in the mountains. So Calgary is a very fortunate city. We have a wonderful, relatively pristine area that generates flow in the rivers that we take from. And you'll see here are the First Nation reserves that are also supplied within the Bow River Basin. And here's some irrigation districts which use the majority of water, as they do in many areas, irrigation worldwide. And then there's a number of communities further down where the Bow joins with the Oldman to become the South Saskatchewan River. And the Bow has some significant seasons. So we have strong winters in Calgary, and during the winters, which pretty much go from mid-November, so you can start skiing if you're lucky in late November, all the way until April. You can see that the last ski resort, alpine ski resort in the Front Ranges or the eastern slopes here, makes a point of closing on the first so-called summer holiday weekend, which is May 24th weekend. And so during this winter, the flow, you can see here it is at Lake Louise, at Banff, which is up in the, I should have put that on this slide here. So Banff, which is right about here in the watershed, and Calgary are the two stations here. So in Banff, the flow is quite a bit lower than it is at Calgary because there's all the flow generation between Banff and the edge of the mountains. So you can see that the winter base flow season, which has the lowest season here, it's about 8 cubic meters a second. In Banff, 45. In Calgary, the average flow in Calgary is about 85 or 90. And so during this low winter flow, almost all of the water that is being used for water supply comes from groundwater that has been stored in the mountain watershed and released. And then we start here, and this is the snow melt season, so lower elevations start melting sooner, higher elevations melt later. And it's the snowpack is really tangible. Like you look up and you can see it from Calgary. You can see snow in the mountains. And it's widely held that if you have a high snowpack, you'll have enough flow in the summertime. And if you don't have snowpack, you won't have enough flow. But what people tend to forget is that our rainiest months are May and June. And so the flow increases because of snowmelt and also because of precipitation. And this is our flood season. We had a particularly destructive flood in 2013, so more than a decade now. And we had a look back at the historic data available. And ironically, even though people look up at the mountains and see snowpack and think floods are caused by snowpack, in fact, it's much more strongly related to the amount of rain and sustained rain. So that's a misperception that floods are caused by snowmelt. In fact, they're caused by rain and, of course, rain on snow sometimes. And this increasing flow is fortunate because that's when the irrigation canals open for the season. The high irrigation season when farmers use the most water on their fields is concurrent with periods of high flow. And then after the snow melt is completed, then the glacier melt will start towards the end of the summer, and we'll talk a little bit more about that soon. And then there's a period of recession and we go into winter flow again. Okay, so just to show you that flow generation happens in the mountain, here's the average flow that happens in Lake Louise up here and in Banff. So this is average annual discharge in cubic meters per second. And this is the distance from the headwaters, Calgary being somewhere between 200 and 250 kilometers from the headwaters. And so we have Lake Louise, Banff, Seavey, which is pretty close to the edge of the flow generating region or the edge of the deformed belt, Ghost Dam, Cochrane, and Calgary. And you'll see that from its true headwaters all the way through the mountains or the flow generating reach, it tends to increase. And then after it leaves the mountains, it tends to flatten out. So there's lots of generation up in the mountain reaches, flow generation, and much less as it flows through the lowlands, which we call the prairie here in Canada. And I want to take you next to what I thought when it came out in the mid-2000s was the most wonderful knowledge extension or educational piece from our Canadian Geological Survey of Canada. And I still think it's super wonderful, but I have increasing concern with one square here that I'm going to show you. So this is the Bow River Basin waterscape. And this one square here talks about the source of water in the Bow River. And I think it set the stage for there to be a general understanding that 80% of the water that made it to Calgary was snowmelt and 20% was rain and groundwater and glacier melt. And I want to show you some work that we have done that suggests it's more like 2/3 of it is from groundwater and 1/3 of it is from rain and snowmelt and glacier melt. And so I'm not going to show you the collation of data here, very much of it, but to say that the precipitation that falls as rain in the mountains, which receive much more precipitation than the lowlands, versus snow, and here it's put as snow water equivalent, is pretty poorly constrained. So in this whole upper watershed, we have 7 stations where mostly the provincial government is measuring snow water equivalent and rain as a fraction of total precipitation. And that data collection is somewhat challenging. And you'll see here that the higher the elevation, the lower the percent of precipitation as rain. So up in the high ranges, 70% of the total precipitation is as snow. In the lower elevations, it's more like 70% as rain. So if you take these 7 stations, 40 to 60% happens as rain and 40 to 60% happens as snow. And so already that's got some flags for 80% snowmelt here. And I'm going to go ahead now and walk you through some of the work we've done. But first, I want to tell you just a little bit about the subsurface here. So the Rocky Mountains were formed, if you can imagine, when the tectonic plate that has North America on it was sailing west and being compressed in a subduction zone. And so all of these initially flat-lying rocks were pushed together and caused to thrust up on top of each other. So this is just a period from the start until the end. So you start up here, you go down, you start up here and you keep going down, and you'll see that the rocks continually to get crushed together with movement just about as fast as our fingernails grow. And so we end up with the rocks stacked up on top of each other because of the tectonic compression. And we have eastern main ranges where the water flows west. The western main ranges are off this screen. That's where the water flows west. We have the eastern main ranges, and then we have front ranges and then foothills, and then this is the lowlands here. And I'm going to talk to you about mostly the front ranges. So here's where the main ranges are, and here's where the front ranges are. And the main ranges are up in Lake Louise here, and they have a different kind of geology that we haven't really characterized the groundwater sufficiently yet. We're working on that. But in the front ranges, which are this Elbow River tributary here, there's only 2 main kinds of geology. It's a little bit simpler, and that's where I'm going to focus on talking to you about today. So the Elbow River here flows from the top of the front ranges and it flows through a little hamlet called Bragg Creek, and it's got its elbow before it flows into Calgary. And, you know, Calgary was formed because a military dude was sent out to make a Fort Calgary, where the Elbow River joins the Bow River. It's also a historic meeting place for Indigenous communities. And the Elbow River has a really special status that I would be really interested in hearing if anybody can tell me differently. For about 25 years, a colleague of mine has been saying that the Elbow River is the only river that they are aware of whose major end use is drinking water supply. So it's a tenth the size of the Bow, and it supplies 40% of a city of more than 1 million. So its average flow is 8 or 9 cubic meters per second. It supplies Calgary, and then there's a little bit that goes back into the Bow. So pretty special river, and I'm going to talk to you today about the reaches that are in the mountains, which are, of course, the flow generating reaches. Here's another picture of the same geology with different colors, and there's only two main types of geologic formations. And the blue ones here are what I call the carbonates cliff formers, and the yellow ones are the siliciclastic. So they're shales and sandstones. And in the mountains, they form shoulders. And so the cliff formers are blue here. It's hard to get a shot so you can see it, but this is a very famous mountain that you see when you drive the Trans-Canada Highway. And so this is a carbonate cliff forming unit called the Rundle. And then there's shale and sandstone siliciclastic, which forms shoulders, so it's not a steep slope. Another carbonate cliff former, the Palliser. And this is known as Cascade Mountain, and one of the reasons is because there's a waterfall that comes off, which is groundwater, which flows all year round and was well known by the Indigenous communities over the time immemorial that they have been here as a place that they could get water supply in the winter. Okay, and a close-up here of what a carbonate cliff former looks like and a siliciclastic shoulder looks like. So if you were walking up, this would be a lot steeper than this, and which would be less steep than this. So two kinds of unit that the rain and snow melt infiltrates into, goes into various flow paths of different lengths, and supplies creeks and rivers and lakes downstream. So this is some wonderful work that was done by Eowyn Campbell as part of her PhD thesis, and this really has formed some of the foundational work that is part of the Eastern Slopes of the Rockies Rivers project now. And she used two major solutes that are present in water to differentiate between the carbonate cliff forming groundwater, the siliciclastic shoulder groundwater, and interflow, which could be rain or snowmelt or groundwater that has only spent a very short time in the subsurface. So this is sulfate concentrations here, and sulfates are formed when rocks, when carbonate rocks are formed. And so higher sulfate is consistent with water that has had rock-water interaction with these carbonates. And I'm not showing it here, but she confirmed that this was carbonate-derived sulfate by looking at the stable isotopes in the sulfur and in the oxygen. And so these points here, which Eowyn used to create an end member for carbonates, are from springs that come, groundwater springs that come right out of carbonate units, or groundwater wells that are completed in carbonates. And so we can say quite comfortably that water in this area came from groundwater that has flowed through carbonate rocks. And then similarly, these are groundwater for siliciclastic end members. And then really low concentrations, precipitation, very shallow groundwater looked like looked like this. So it had very low sulfate and very low silica. So not very much rock water interaction. And here is where the river samples fall. And so, in fact, they form a trend that goes from interflow, so recent snowmelt or recent precipitation, increases and goes towards carbonate, the carbonate end member, with the exception of some really local flow systems that are only contained within siliciclastic rocks. So we can now take every one of these main stem Elbow River samples and tell you what percent comes from rock water interaction with siliciclastic rocks, what percent comes from rock water interaction with cliff forming carbonates, and what percent is interflow or recent snowmelt or precipitation. And we have the fortune of 12 years of record, and in fact, we've now extended this to more in the Elbow River because the City of Calgary monitors its water quality and has made these data publicly available for researchers. And so we can, for every one of their monthly water samplings, mostly monthly water samples, we can tell you what percentage of the river water came from interflow, what percentage came from siliciclastic aquifers, shales and sandstones, and what percentage came from carbonates. And over this whole record, about a third of it comes from siliciclastic aquifers, about a third of it comes from carbonate aquifers, and somewhat a little bit less comes from interflow. So from this, we conclude that of the flow in the Elbow River, the only river in the world that we are aware of whose major end use is drinking water, 2/3 of the flow was most recently groundwater throughout the year. And if we take those concentrations from the earlier slide and we look at them over time, there's actually significant changing concentrations with time. And overall, and this is a different way of saying the same thing. If you look at the earlier years on the same 3 end member mixing model, the earlier years are lighter blues, the later years are darker blues, and we see a trend that is significant in concentration time series and visually evident here of increasing carbonate groundwater with time. So that suggests that the contribution of groundwater is changing on a decadal scale, and more of it is coming from the cliff-forming carbonates, which tend to be present at higher elevations. And so one possibility or one hypothesis is that with climate change, we are experiencing more precipitation as rain because of warmer temperatures, earlier snowmelt because of warmer temperatures. And so maybe there is more groundwater recharge in the high elevation cliff forming carbonates, which is putting more groundwater that flows through carbonates into the Elbow River. And so I want to underline here that if we want to understand how river flow, which is important to lowland water supply, is changing with time, it's important that we understand how these groundwater flow paths and flow contributions are changing with time in a climate change scenario. Now, this is from the Bow River. So the Bow River, which goes up into these rocks in its highest reaches, which we haven't yet characterized the groundwater of, which are different from the cliff-forming carbonates and the siliciclastics that we've worked with so far. And if we look at the proportion of discharge at Canmore, and we split it into interflow and siliciclastic and carbonate, we see really clear seasonal changes here. So roughly a third of each in the wintertime base flow, that's the lowest flow, more interflow, snowmelt and recent precipitation during the high flow spring and summer, and glacial melt period in August here, and less carbonate, but maybe a little bit more siliciclastic initially in the high flow period. So there's a pattern here that is related to the groundwater flow paths and the different proportions that reach the river seasonally. Okay, so I hope that I have shown you evidence right now that the river water in the Bow River watershed is mostly from groundwater. That is the old water from the old water paradigm. Clearly seasonal differences in groundwater source contributions, and groundwater contributions are changing on the decadal scale, which is not yet incorporated into our flow prediction models. And the last thing I want to show you here is that groundwater is not significantly tied to the fate of our glaciers. Our glaciers are our most iconic and beautiful landscapes, and I lament the fact that we are tangibly using them as much or possibly more than anyone. They have unique ecosystems, but I think there's a little bit of hyperbole about how important they are to river water supply. So I already showed you the Elbow River watershed. This is the only glacier in the Elbow River watershed. This is from a 1990 publication on glaciers of the world here. And already in 1990, it was a hanging glacier. Here's the glacial ice here. It was a few hundred meters long. And this is a few years ago when I was up in the watershed in November, and I could see the hanging glacier, and honestly, it was so small and unremarkable, I didn't take a picture of it. Rather, I took the watershed looking the other way. So pretty much I'm standing where this photograph was taken, but looking downstream. And so this glacier is disappearing in a river, which in this 2022 paper, which is the one that talks about the fact that floods are produced by rain and not by snowmelt, we found that over the period of record that the Elbow River watershed was receiving more precipitation and had more flow. So I'm comfortable saying that the flow generation in the Elbow River watershed is not related to glacial loss. Here's a summary of some work done by glaciologists that show that the Bow River, the estimates of the Bow River, the amount of Bow River flow annually that is from glacial melt, which happens mainly in August, it ranged from about 1.8% to 2.8 or 3%. A little bit of a concern here, two concerns. One is that glacial melt is defined differently in different publications. And the second one is that all of the water that comes out into the proglacial environment is assumed to be glacial melt, and groundwater is not considered. And I'll show you just a bit about that shortly. And in this case, you know, what glaciologists say is that the contributions of glacial melt to stream flow has already peaked in the Canadian Rockies, and that the amount of glacial melt is quite difficult to measure. And finally, in terms of water supply from a very practical point of view, the glacial melt happens when we're on the falling limb from seasonally high water supply. And so there's plenty of water at that point in the absence of glacial melt. And this is some work that was done by Kevin Sevelrud for his bachelor thesis, and it's being followed up by a master's student right now. And this is the component of groundwater contributions. This shows the component of groundwater contributions to the proglacial environment that feed the downstream streams that is not considered very often by glaciologists. So I beg your pardon. So first of all, they often don't recognize that the highest parts of the elevation are not snow covered, so there's groundwater recharge above this. And second of all, anything under the glacier that comes out in the proglacial environment is assumed to be glaciers that are melting, as opposed to potentially groundwater discharge underneath the glacier. And third of all, that this mountain block, if you will, continues to supply water below the glacier. And so we're working now to try to understand how much of the proglacial streams coming out of the glacier are from groundwater. That's part one. part two is that in the high elevation, those are where the main stem river flows are the lowest, and so it's a small fraction of a small amount of the river before it leaves the mountains. I hope you followed that. Okay, so I hope I have now shown you these 4 points here. And I'd like to underline this with the fact that predicting future river water supplies really will benefit from understanding how groundwater contributions are changed. And it's incumbent on me to work with surface water people and vice versa. You might ask yourself, why doesn't groundwater get the attention I think it deserves? And, you know, it's in the subsurface, it's expensive to get information, you can't see it, it's not visually tangible, it's complex because geologic formations are complex, it's spatially and temporally variable, and it requires inherently interdisciplinary work, which is hard to do, but we need to do. And I think it's summed up very nicely by a YouTube video that I watched from Jeff McDonald, in which he talked about how complex it was, and then he used the screen picture to show what the field of studying subsurface groundwater flow is like. And before I thank you for joining me, I just want to make the point that I want to reiterate the point that groundwater is super important in so many parts of the world, underappreciated, and in particular in semi-arid parts of the world. These little groundwater ecosystems, groundwater dependent ecosystems, are hugely important, and I encourage you to consider groundwater if you're a groundwater scientist. My take home points are mainly that we need to work together. We need to use multiple lines of evidence, so not just differences in flow, not just water isotopes, but also solute isotopes to understand how river groundwater contributions are changing, for instance, and that the need to do this, I don't believe, has ever been greater. And I'll end with a shout out to the Eastern Slopes of the Rockies team that have supported all of this work, and also thanks to Grace and her team for organizing and for the invitation, and finally for everybody who joined today. I assume that Grace is going to come back on.
Definitely. Thanks so much. That's quite revealing. It's quite revealing. I guess a couple of things jumped out to me or at me in your presentation. You know, the saying that out of mind or out of sight is out of mind, you know, seems to play so well with this issue of groundwater. And that to me is quite interesting, that we need to now start to, in a way, placate, appeal, you know, to people to appreciate this huge resource that has actually, you know, been a center of life, especially in a lot of places where the only thing available to you, especially where you don't have government infrastructure, you know, that pretty much the only thing, you know, accessible to you is actually groundwater, you know. So it's a bit like a paradox to me, you know, but I appreciate the presentation. And quickly somebody saying, well, thank you for the talk. What can we as concerned citizens do to both help preserve these critical groundwater resources and help raise awareness about their importance? Question for you.
Well, thank you, Miriam, for that question. And I have a lot to say on this topic because I found myself with some other groundwater scientists in the International Association of Hydrogeologists Canada chapter, all just marveling at how little attention our federal government was paying to it. So I thought a lot about this. And I think that there's a distinction between the water supply, the water distribution, or the system of pipes that brings water to houses and industries versus the resource. And so, for instance, Calgary, a city of 1 million, had a catastrophic pipe break in June this year, just a couple of months ago. We had a water emergency, and the whole city was being supplied by this little Elbow River. And that pipeline was Calgary's property, and it was Calgary's problem to fix. But if the river stopped flowing tomorrow, everybody would look at the government and say, where's the river water? The same thing applies to groundwater, but this isn't understood. So the well infrastructure, if you dig your well, if you drill your well, that's on the homeowner. That is their water distribution system. But if the water level in the well goes down, then I think it's really fair to look at the government and say, this is a resource that the government manages. What's happening to the groundwater? So there is a trend in watershed groups in Alberta to actually start monitoring their own groundwater in the absence of government monitoring. You can't manage what you don't measure. So what we can do is look to governments and say, this is what's happening with our groundwater. What are you going to do about it? And to be politely persistent about the need to understand and manage groundwater. Yeah.
Oh, okay. Let's find a way of transferring your wealth of knowledge from this case study and this region to those parts of the world where groundwater is actually so significant to their lived experiences, but yet lack the expertise to monitor, these groundwater resources, and they're just taking and taking and taking. What's your thoughts on that?
So I think that the key to okay, first of all, 50% of the world relies on groundwater, and literally the poorest and most vulnerable sectors of the population, which tend to be outside of cities and outside of social support systems, tend to be groundwater dependent. And I think the key is appropriate training programs. So how do you monitor your water level in your well? How do you find out where to drill a well? How do you integrate the monitoring that you've done? So I think, as a UNU water hub in Calgary, that the best thing that we can do to facilitate appropriate groundwater management worldwide is to work to have groundwater training programs at the primary school level to post-secondary level that are widely available and accessible. So there's a couple of initiatives. There's the Groundwater Project, which is in Canada, which has chapters that are free to anybody. Recent chapters written, basically it's an online evolving textbook that anybody can access by searching for the Groundwater Project. And there is a colleague, Dr. Ty Foray, in the United States, who is working to start integrating groundwater courses at the university or the post-secondary level so that they can be available worldwide. So by training the trainers, by training people that would teach groundwater, then hopefully we can enable people to understand and then to be able to lobby with data. You need to have data to be able to say what's happening to a resource.
Yeah, I like that statement. We need to have data to understand, but let's move away from this knowledge-based intervention. It's debatable how feasible or how practical it really is in the context of a lot of intersectionality layered on all this. But I want your quick take on this AI or machine learning approach to generating water quality data versus primary research, primary data, primary water quality data. Because I can see that the models that you showed, the interflow, the carbonate, was primarily based on water quality monitoring and all that. So what's your take on using machine learning or these AI-based approaches now to generate water quality data versus real primary water quality data in predicting or giving us better knowledge about groundwater flow and modeling?
Wow, Grace, that is a pretty difficult question.
Sorry for putting you on the spot.
So I come to this as a field hydrogeologist, and it's a tough life to try to collect real data. It's expensive, and that's why people go to AI techniques, etc. So it's hard for me to say that we can, in the absence of water quality data, that we can generate water quality data. I think if you have enough of it, then you can start working on it, but you need a certain amount of real data to start the AI process, I think.
Okay, so on that note, I'll say let's call it a wrap and allow you to take a breather. So once again, thank you so much, Professor Kali, for being part of the Science Talk. We've learned so much, and I appreciate the way we kind of expose these huge hidden results, putting it back in our faces, that this is so important, it's critical to life. We can't overemphasize the central role of groundwater in our lives, especially in clans, in communities where, life really, literally depends on it. So once again, I say thank you for your time. Thank you, for the presentation. Thank you for the insights provided. And let's see you soon.
Thank you very much, Grace. I really appreciate the opportunity to share my enthusiasm for groundwater.